In this video, I'm going to go through the basic steps of proof by induction and also go through 2 examples just to show how it's done. Proof by induction might seem the most challenging type of proof for students, not because it's hard to do, but because it's hard to grasp and assume that it's a logical proof. I know I struggled with accepting it when I was in school. But it's if you understand all the steps that you have to do and all the basic parts of proof by induction, then you should be on the right track. So proof by induction has 4 layers. Sometimes they tell you 3, but the conclusion is also very important. The basic step is, the idea of proof by induction is you proving it from the beginning, and then proving it halfway through, and then proving that it's true for all the values that you've shown. So the basic step is basically your starting number. You want to show that it's true for your beginning, because if the basics is not true, if it's not true for your base case, then there's no way it could work for all the other cases. Now, the starting number is not necessarily 1. It could be 0. It could be a negative number. It could also be things like 100 or 5, depending on your question. So make sure you read your question carefully and understand which number is your basic step, the first number you're allowed to put in your formula. The assumption is when you go, okay, now that I proved it for the basic step, this is my basic step, I'm going to assume that at some point it's also true for a k here. So we're going to assume that our formula is true for all of these, that it actually worked for all of these up to k. And then the inductive step says that, oh, since it's worked for all of k, then let's try and see if it works for k plus 1. And that's the idea. So if it actually works for k plus 1, using the fact that it worked for all of these, then it's true for every single, then it's true for all the values you're looking for, because k could be anything. K could be in the beginning, could be in the end, could be halfway here. So if it works for k and k plus 1, it means it works for everything. It's like a domino effect. If it works for the this number, then it's going to work for the rest. And then the conclusion is a very specific wording that you have to use at the end of the proof by induction. So this is how the steps are going to go. The first example I'm going to go through is the showing. So this was proof by induction that the sum of the first n terms of an arithmetic sequence with first term u1 and common difference d is given by this. So this is the common formula used for the sum of arithmetic sequences. Now, the sum of arithmetic sequences does have a proof, so you can use that proof. But proving it by induction also works. So for this example, we're gonna label our formula that we want to prove, which is this plus n minus 1 d, and that would be Sn. So for our base case, so when you're doing proofs, you have to label which case you're in. Maybe there are marks, maybe there are not, but for a proof by induction, we need to see where exactly is your base case, where's your assumption, and where is your inductive step. So base case means that we try n equals to 1. So remember when I said that your starting number could be anything depending on the question? So this question, obviously, n has to be an integer, and n would start with 1 in arithmetic sequences. We don't have n0, we don't have n negatives. We start with 1, so that's our starting point. When n is equal to 1, s of 1 is u1. We know this as a fact because we know arithmetic sequences. So again, this assumes that you know what arithmetic sequences are. So let's try p of 1. The reason I'm using p is because some books by convention use p to define the thing you want to prove. So I'm going to stick with that notation. So p of 1, if I just substitute in here, I'm going to get 1 over 2 to u1 minus 1 d this will just be a 0, so I end up with half 2u1, which is just u1. And we have in this case that left hand side is equal to right hand side, so that's what we wanted. Now in proof by induction, you might be using different techniques in between each proof. So in this case, we're doing the whole direct proof where we want to show that left hand side is equal to right hand side. In the next example I'm going to go through, you're going to see that my proof is going to be slightly different. So this is the basic step. We've proved that it's true. Now we're going to go for the assumption. So you have to word it very carefully, and I think this is where students get a bit confused, because why would I use specific wording every single time? Well, this is how this proof works, and it establishes it quite well. So we're going to let n be equal to k. Now the reason I'm not going to use n is because n is used in the formula itself. When I say k, I'm talking about a specific point in the sequence or a specific point in my formula substitution. So it's k is like a stopping point somewhere. So let n be equal to k, where k is in this question, it's a positive integer. It's only positive because we're talking about arithmetic sequences. So we're going to assume that pk is true, where pk is k over 2 u1 plus k minus 1d, which is sk. So you can say assume Pn, we can rewrite this as assume Pn is true up to n equals to k. And that's how you've established this. Now, the assumption is not just a random thing. We want to use this result in our inductive step. We have to use this in order to prove our inductive step. If you don't use this in the next step, even if you've proved the correct thing, but if you haven't used this, then you are not doing proof by induction. So this is the most important part right now. So now that we've done the assumption, we're going to go the inductive step. Again, as I repeat, we will have to use the previous result. So we're going to let n now be equal to k plus 1. So we're moving to the next one. So Pn is now pk plus 1. And we're not going to substitute k plus 1 in the formula, because here's the deal. I'm going to go down. What we want to get to after proving everything, we want to get to k plus 1 over 2 u1 k plus 1 minus 1d. This is what we want to get to. We want to show that if I actually use my previous result, I'm going to end up with the same formula that I was meant to use if I substituted. This is where students go, well, I could just substitute k plus 1 in here and I haven't proved anything. Well, it's the idea of using everything you've built up to get to the result that you want to show that actually this is consistent for k plus 1, k plus 2, it's all going to be consistent. So we want to get to here. So we know that pk plus 1 is basically sk plus 1. So that's the definitions we've been using. And sk plus 1 is just basically sk, so you adding up up to sk, and then adding your last term. Again, this is on the basis that you understand arithmetic sequences. So this is you then adding uk plus 1. Now we have a way of defining uk plus 1. We are assuming that the formula for arithmetic sequences is true. So this is just u1 plus k plus 1 minus 1d, which just simplifies to kd. Okay, revise the formula for arithmetic sequences to get this part. Now, this is where you will use your inductive step. So you need to write you're going to use the assumption, sorry. This is where you rewrite the inductive step as if you're trying, you rewrite the inductive step where you're going to have to use the previous result. So we're going to use our previous results and we're going to write it as k over 2 2u1 plus k minus 1d, and then our u1 plus kd. So then all you have to use is just algebraic manipulations. So you can pause this video and try it on your own to see if you can get to this, and then unpause the video to see how I end up doing it. So I first expand out, so I'm gonna get 2ku1 over 2 plus, if I am gonna keep this just to keep it simple, kd over 2 and then k minus 1 plus u1 plus kd. This will simplify to ku1 plus, I'm just going to collect the like terms together, the u1 terms together, and then this will be k squared d over 2, so this is here, and this is minus kd. I'm also going to multiply, so I'm taking these two. I'm going to multiply this by 2 in the numerator and denominator just to get a 2kd over 2. And so I'm going to bring it here. We might need more space, so I'm going to move this lower. So simplifying this, I can take a factor of u1 out, so I end up with a k plus 1. Now it's always good to go down here and see what are you expected to get. Now notice how there's a factor of k plus 1 over 2 out. Well, at least I have a k plus 1 here, which means what if I get a k plus 1 factor out here as well? Let me simplify this first. Sorry, I forgot the 2 here. So if I simplify this, I'm gonna get plus kd over 2. So this is u1. And then I could take a factor of kd out, so k plus d, which leaves me with k plus 1. And notice how I now have the 2 factors out, so I can take them out. And then whatever's left goes into the bracket, so u1 from this term, and I have k plus d on this side. Again, I'll need a bit more space. So obviously not too close to here, we still have a factor of 2 out. So if I take a factor of 2 out, 1 over 2, then I'll have to multiply this by 2. And then this will stay as k plus d. Sorry, no, it's not a factor of k plus d. Hopefully you've spotted that. It's a kd factor. So this is kd. So you take a factor of k out and d out. I was thinking about the brackets. So we have kd without the over 2 because we've taken the factor of the half out. And this can be rewritten as 2u1 plus, well, it's k plus 1 that we're looking at. So k plus 1 minus 1 d. So these two will cancel out, but this is what we want to get to. And then your conclusion. So you don't have to write conclusion, but it's good for you to remember. So you have to say something similar to the wording of since P1 is true, so that's your base case. Also, if, because that was your assumption, if pk is true, then Pn is true for n equals to k plus 1. So we realize that k plus 1, pk plus 1 is only true if pk is true, because we assumed that pk is true. So then you end it by the principle of mathematical induction. The statement, you can write Pn or the thing itself. Is true for all n in the positive integers. And hopefully that is clear. There is one more example I'm going to go to. I know the video is spanning a bit long, but it's the length of proof by induction. So this is slightly different because there's no assumption like the sum of integers or anything. So if I want to show that 9 to the power of n minus 1 is divisible by 8 for all n in the integers. So my Pn in this case is 9n minus 1. And what we want to show is that 9n minus 1 is divisible by 8, which means that it's equal to 8 times something, or that something is an integer. So whenever you look at divisible by a number, then just rewrite it as such. So you can say we want to show Pn. I'm not going to write it again. We can say that this is what we want to show for a m here. So our basic step. So notice how n belongs to the natural numbers, and I'm assuming for the Oxford IB book, n cannot be n as 0. So our inductive step would be n equals to 1. So p of 1 would be 9 to the power of 1 minus 1, which is 8, and which is divisible by 8 for obvious reasons. So then we go to our assumption, and we say let n be equal to k. So assume p of k, which is n to the power of k minus 1, is divisible by 8. And so I can rewrite this as something like this, where m is an integer. Now we go for our inductive step. And I say let n be equal to k plus 1. And so I have p k plus 1 is equal to 9k plus 1 minus 1. Now, sometimes you can prove this without using your assumption, but remember, we want to use this assumption. We want it to fall nicely in there. Now, rewriting this would be 9k times 9 minus 1. Now, looking here, it would be amazing if I could extract this 9k and this minus 1 and just substitute 8m, but I can't. Right now, the 9k is stuck to the 9. So what if I rewrite this? So I could say, using the assumption, 9k is actually equal to 8m plus 1. So notice how if I rearrange this, I'm going to get 8m plus 1. So I am going to use my assumption, and that is what you want. As soon as you use your assumption, you're on the right track. So 9k is just 8m plus 1. times 9 plus 1. So this is going to be 72m plus 9. Sorry, not plus 1, minus 1. Minus 1. So this is 72m plus 8. Hopefully you've spotted that you can factor out. So this is 9m plus 1. Now it doesn't matter what this is, but it's divisible by 8. So we've shown that 9k plus 1 minus 1 is divisible because it's equal to this, so it's divisible by 8. And so your conclusion will be since it is true for n equals to 1, or the base case, and if the assumption is true for n equals to k, then n equals to k plus 1, so p k plus 1 is true. Hence, by mathematical induction, Pn, which is, or you can write the full statement, so 9n minus 1 is divisible by 8 for all n, the natural numbers. Notice how my wording of this statement is slightly different. You can't stick to the one given to you by your book or publication. You just have to address the fact that you've done the base case. You have to address that if the assumption is true, then it is true for your k plus 1 case, so for your inductive step, and then you have to conclude it by mathematical induction, and then go back to your actual statement. Hopefully this was clear. So again, the idea for proof by induction is just to follow these steps and just make sure that you use the assumption in your inductive step and then write your conclusion in the end.